That section of the calculation is called dynamics, when you introduce actual forces to make predictions of future motion.
The prediction of motion involves quantities that we discussed before, distance, velocity, time. In addition, you have quantities that are characteristic of whatever you're measuring. So mass, force, moment of inertia, charge, Q, all of these things are particular qualities of motion. In kinematics, you only trace the path or the trajectory of motion. In dynamics, you must include mass and force and force and force.
Kinematics primarily deals with coordinate acceleration, while dynamics considers proper acceleration as the true acceleration reflecting the influence of forces. Proper acceleration is experienced by an object independent of any particular coordinate system. It is measured by an accelerometer and represents the actual change in velocity due to forces acting on the object, making it a dynamic quantity.
Yeah. Oh, here's a good summation of the Newton's bucket. Here's a great way to another way to look at it. Here we go.
Reference frame. Now, I tried to update this experiment by doing something that's more familiar. Newton's bucket, the experiment is named after him, so I'm going to call this Bennett's hiker. We have, first of all, a hitchhiker frame, which is the same as the lab frame. If you have a car accelerating towards you as a hiker, and you ask, what do the laws of physics predict? Then the prediction is the force on the driver, Fd, is equal to the mass of the driver times the acceleration. So Newton's law says the driver should have a force exerted on it. And we all know this is true. If you're accelerating in a car, you can feel the car seat pressing on your back.
If you're inside a car and the driver steps down hard on the gas pedal, causing acceleration, you will feel as if you're being pulled towards the back of the car. This feeling of being pulled backwards is your body feeling proper acceleration.
And you could measure it with the appropriate equipment. So if you are in the hitchhiker frame, which is the lab frame, Newton's law is correct. Suppose you use the reference frame of the driver. In the driver's frame, you see the hitchhiker accelerating towards you with minus a acceleration, and you want the force on the hiker to be equal to the mass of the hiker times his acceleration. All right, the calculation shows that this is not zero. But we know that when a car passes you and it's accelerating, you don't feel any force. You may feel a slight breeze from the air that's moving past the car. But unlike the driver, anyone stationed in the lab frame will not feel any force.
Proper acceleration is experienced by an object independent of any particular coordinate system. It is measured by an accelerometer and represents the actual change in velocity due to forces acting on the object.
Now I tried to update this experiment by doing something a little more familiar. Bennett's hiker is named after him, so I'm going to call this Jason's hammer.
Dropping the hammer! No, you're not!
First of all, we have the hammer frame, which is the inertial frame. If you have a toolbox sitting on the ground accelerating towards you as the hammer, and you ask, what do the laws of physics predict? And the prediction is the force on the toolbox, Ft, is equal to the mass of the toolbox times the acceleration. So Newton's law says the toolbox should have a force exerted on it, and we all know this is true. If we are standing on the ground next to the toolbox, you can feel the ground pressing on your feet, and you can measure this with the appropriate equipment. So if you're in the hammer frame, which is the inertial frame, Newton's law is correct. Now suppose you use the reference frame of the toolbox. In the toolbox frame, you see the hammer accelerating towards you with minus a acceleration, and you want the force on the hammer to be equal to the mass of the hammer times its acceleration. The calculation shows this is not zero. And we know when a falling hammer passes you and it's accelerating, free fall, you do not feel any force. You may feel a slight breeze from the air moving past the hammer, but unlike the toolbox on the ground, anyone in the free fall frame, inertial frame, will not feel any force.
That section of the calculation is called dynamics, when you introduce actual forces to make predictions of future motion.